Hi everyone, this is G. Muthuram, Assistant Professor in the Department of Electrical and Electronics Engineering, Hindustan College of Engineering Technology, Coimbatore. And in this video, we are going to discuss about the switched reluctance motor and drives in special electrical machines. As you know, this is the pictorial diagram of the switched reluctance motor with the stator and rotor arrangements. It is a 12 stator teeth and 8 rotor teeth. Features of the SRM. The first SRM was built in 1838, but it was not so popularized because of that controllers were not developed in that period. So it was popularized only after the late 1970s with the advent of the power electronic devices and the power electronics controllers. And according to the construction, the SRM is doubly salient and it is a singly excited machine. That means the stator only having the coils and the rotor has only steel laminations. And also the coils with an independent windings on the stator. And rotor is a simpler because there is no kind of any windings and permanent magnets. The stator windings, which are placed in a diametrically opposite poles, are connected in series or parallel to form one phase of the motor. There are several configurations in the stator and rotor assembly. Examples are 6 by 4, 8 by 4, 10 by 6, and 12 by 6, etc. That means when you are taking that 6 by 4 means 6 stator teeth and 4 rotor teeth. The configurations of SRM with higher number of stator or rotor poles having less torque ripples. The stator poles have concentrated winding rather than sinusoidal winding. Each stator pole pair winding is excited by a converter phase until the corresponding rotor pole pair is aligned and is then de-energized. The stator pole pairs are sequentially excited using a rotor position encoder for timing. The SRM which are used in the closed loop, therefore we need an RPS, that means rotor position sensor. That sensor will read that information and it will pass to the controllers. So the controller will give which stator poles is to be excited. That will be decided by the controller as well as the feedback devices. And the pulsed nature of the torque production, which leads to torque ripples and acoustic noise generations. These two are the worst case of the SRM. That means the torque ripples and acoustic noise are the drawbacks or degrades of the SRM. So to have high torque volume ratio leads to less manufacturing tolerances and increased acoustic noise. And I can give you that advantages of the SRM. It's a very simple construction and also it has a robust construction too. And there is no windings on the rotor of the motor. You can see the pictorial diagram which is near to that, and it has high torque inertia ratio and maximum operating speed and rotor temperature because there is no kind of any permanent magnet or coils over the rotor. Therefore, it gives an high speed operations. Each phase winding of the SRM is independent of the other phase winding. You can see the diagrams also. And the applications of the SRM, it was developed in recent days for electric vehicle, that is automotive applications. And also it supports in the industrial drives, well established in the robotics also, the position servo applications, machine tools. And the different configurations of the SRM are 6 by 2, 6 by 4, and 8 by 6. That means I already mentioned that 6 by 2 means 6 are the stator teeth and 2 are the rotor teeth. You can see the diagrams. And these configurations, it will give you a very good rotating of that. That means you can see that diametrically opposite poles are excited by the respective controllers and that sequential may be changed with respect to the controller output. Therefore, the rotor will follow that excited stator teeth. Okay, so that is the working of this 6 by 2 SRM, and the blue pictorial diagram will show you that 6 by 4 working. And this is the simplest diagram about the 6 by 4 SRM, phase A, phase B and phase C. There are three set of coils which are independent with each other. Phase A coil is not connected to the phase B and phase B coil is not connected to phase C. And the inductance is chosen by the rotor position. So the variation of the inductance is the very important in the working principle of this SRM. Okay. And then next one, I will show you that how the rotor is aligned with the excited stator. So the stator has a coil, it is energized. Whenever it energized, that may be acts as an electromagnet. Therefore, the rotor, which has no permanent magnet, which has no winding, therefore it is a simple steel laminated core structure. So that core will be attracted by the excited stator winding. Okay, and you can see the inductance of the stator pole pair and the corresponding phase current as a function of angular position. Therefore, whenever the rotor is changed, the inductance is also varied. So the inductance will goes to maximum and it will come to that minimum. So there are two positions are there. Whenever that stator teeth and rotor teeth are in aligned positions, the inductance will be maximum. For each and every phases, you can notice that phase A, phase B and phase C. So respectively, we are sequentially energizing the coils. Therefore, it attains its maximum, that means the peak value, and it will come to lower value. And this is the SRM drives. So there are four modes are there: inert, freewheeling, defluxing, and also that fluxing. So that inert means it's nothing but it is connected across the supply. Fluxing means the flux will be developed in the respective coils and the two switches are acting on that. Freewheeling in the sense the stored energy will be dissipated to the supply through that same switches. And the last one is concept defluxing. That means de-energizing the respective coils. So there are four modes are there in the drives. So first one inert, second one fluxing, and the third one freewheeling, and the fourth one is defluxing. So these four modes are very important in the SRM drives. And the next case, you can see that there are two degrades which I already mentioned, that acoustic noise generation and the torque ripples. So this, so the SRM drivers, so the SRM drivers have the two degrades are there: acoustic noise generation and the torque ripples. So by changing its magnetic design or by choosing the proper converter, so that it has a two degrades, acoustic noise generation and torque ripples, it will be reduced by the two techniques. The first one is changing the magnetic design of SRM, and the second one is choosing the by choosing the proper converter topologies. So we have to enhance the performance of the SRM by two methods. And somewhat the comparison of the SRM drives. We are using n number of converters like asymmetric bridge converter, CDUM converters, resonant converter, two-stage power converter, and also ZVT and ZCT, that is called as zero voltage and zero current soft switching techniques. So by comparing that, that may be suitable for low power applications or low speed applications or high speed applications. So depends upon our application, we can choose the appropriate controllers or and converters. And this is the another waveform, and the choosing of the brushed DC motor, universal motor, asynchronous motor, synchronous motor, switch reluctance motor. So why we are choosing this motor as a traction purpose, and why we are using this in the automotive washing machines? So n number of comparisons are mentioned here, and these are all the some kind of photographs about the SRM. So the handling unit, the weight handling unit in the paper mills or in the rack, somewhat it is used in the uh, buses also. Therefore, the HT lines we are using in this e-vehicles also, the battery vehicles are using this SRM. Okay, thank you. Thanks for your listening. Thank you.